原宣多媒体报道，9月23日太平洋时间上午11点，少数族裔媒体服务中心召开网上会议。会议的主题是探索外太空。我们为什么要这样做？我们学到了什么？詹姆斯·韦伯空间望远镜最近带给我们一些旧的恒星和星座的新影像，让我们的脑子立刻充满了惊奇。看着这些图片，其中最具有影响力的影像，我们讨论小组成员中的一人写道：这无止境丰富的深空奇景挤满了恒星及星系，虽然它只覆盖着一小片天空，却讲述着整个宇宙的历史。这些影像也让我们充满了疑问：在宇宙中是否还有其他的生命体？什么种类？其他的行星是什么样子？在将来，我们会去月亮及火星做定期旅行吗？现在，包括美国在内的几个国家正在探讨类似这样子的所有问题，已经在几个不同的项目及科技中做了投资，希望能够帮助我们探索自己星球以外的宇宙。其中一个更大的问题是，宇宙的探索能否从各方面帮助人类寻找一些基本问题的答案，包括找到我们在地球上生存的钥匙。为了探讨这些议题，本次会议我们请到了一个非常杰出的讨论小组。参加本次会议的专家有科学与技术传播者亚历山德拉德、卡斯特罗，马里兰州巴尔的摩太空望远镜科学研究所首席天文光学科学家马西奥·梅伦德斯，马里兰州巴尔的摩贾科尼太空望远镜科学研究所博士后研究员尼可·阿鲁兰达姆。
6 months, about 3 to 6 months, and they will use the Orion modules back and forth from the Earth, and some vehicles for food and supplies. And of course, they will have the lander so they can go actually to the moon and work on the moon, and many robots which will help with the heavy work, right? So this is a medium-term plan. And as I said before, in the end, what we want to know, what we want to achieve is to learn a lot about the moon and how we can build a base to stay on the moon, a base on the surface, okay? So why are we doing this? So this is what we are here to discuss. Why are we doing this? What are the benefits for society of human space exploration and astronomy as well? Well, I have this here, this picture I took from Wikipedia. This is the Beagle. I don't know if you remember this, the name of this boat. This is Charles Darwin's boat. He explored the whole planet. I mean, not the whole planet, but he and Humboldt and many others explored many places on the Earth. And they found many new species and clues about life on Earth in such a way that Darwin could propose his evolution theory. And actually, evolution is not just a theory, it's a fact. It's something that is happening right now as we speak. So, and what is this? Is curiosity, is we're hungry for knowledge. We want to know many things. And this is what makes us humans, actually. I would lie if I would say something like we are going to space because we want to do something good for a society. We are going to galaxies. So our galaxy, which is so big, is not unique. So this is a knowledge that makes you think. Also, we have other perspectives from us, from the Earth, from the Moon, for example. This is the Earth from the Moon taken during one of the Apollo missions, and this one here is the Earth taken by Cassini when Cassini was orbiting Saturn. And well, this is my favorite, I guess. Here is this very little faint point is the Earth. This picture was taken, this is our very first selfie. It was taken by the Voyager 1. And Carl Sagan was inspired by this picture, and he wrote a speech which is called The Pale Blue Dot. And if you haven't heard the speech, you should, because it's beautiful and important, I think. And I have a track here, and I want to read it for you. The Earth is a small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals or emperors, so that in glory and triumph they could become the master of this fraction of a dot. Our imagined self-importance, the delusion that we have some privileged position in the universe, is challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. This is beautiful. And
keeping a good time on the presentations, I realized that I have this challenge of talk about the whole history of the universe, 13.5 billion years in 15 minutes. So let's see how we do it. And I'll try to follow what Alexandra was mentioning on why we do some of the things that we have, right? And with the James Webb, right, there are a few things like how can we solve some of the most fundamental questions that we have? Where do we come from? How the universe was formed? And how do we get here, right? Is there life outside our solar system or even inside the solar system, right? So for those things, we need to think big, right? And there is nothing bigger than the James Webb. And we're gonna start with just a few key facts. And don't worry, I'm just gonna show many of the images, and we're gonna go through many of the new discoveries that Webb have made in the past a few months. But I just want you to spark a little bit of your imagination, right? Thinking about a telescope that is so sensitive that you could see the heat signature of a bumblebee at a distance to the moon, right? So what would you do with something that is so sensitive that you can do that, and that requires such a high level of precision that we are moving, each of these mirrors need to be aligned of a 1 of 10,000 the width of the thickness of a human hair, right? So those are the levels of precision and sensitivity that we need to answer those fundamental questions, right? We're trying to go back as a time machine, right? We have a golden, almost robotic telescope in space that is looking back in time to when the universe was formed. So let's start from the beginning. So the James Webb is a telescope, a space telescope that operates in the infrared. So it has to be very cold. We're gonna talk about in a second in the next slide, why the infrared and why the infrared is so important. Then, very important, is the first segmented telescope in space. The primary mirror, you can see in the slide, is 6.6 meters across, and is composed by 18 different segments. Why it is important that these have to be the first segmented telescope in space? Remember that for a telescope, if we think a telescope, we need to collect light from the universe, right? So imagine if you have a bucket of water The bigger the bucket, the more water you will. Glasses that I'm wearing, right? These are the light that is coming from the galaxies that are behind that cluster of galaxies, what we call gravitational lens. So you see all those arcs. You see the arcs of these on this picture. This is the central part of the global cluster, and you see sort of like these arcs. So basically, that's light that is passing from behind the objects that are behind that cluster of galaxies that are bending, right, because of the gravity, and they're reaching us. We can reconstruct that light, and now we have a way of measuring and observing these galaxies that are far, far away, way behind this cluster. And from this, we know that these are some of the early galaxies in the universe, when the universe was only 1 billion years old, right? So for this, we can say that the blue galaxies, this is a color image using different filters with James Webb, and each filter represents something. So we can see some of the blue galaxies. We can think about those having a lot of stars, forming stars, young, a lot of radiation, where the galaxies that are red are galaxies that have more dust, and this is where we're seeing those enshrouded galaxies. And we observe this with 4 instruments on top of the James Webb, and we use the spectra. The spectra of that is basically just imagine the rainbow that you see outside every time it rains. Well, we're looking at the rainbow of this galaxy, how the light separates into all these colors, right? And when we do that, we find things like this. Well, we use the near spec. We separated the light of this galaxy, and we identifying common elements, right? Remember, the beauty about science, right, is that we study here hydrogen, helium, all these elements, but those elements behave exactly the same way here on Earth that in these distant galaxies, right? So we know the properties of those elements here. We can identify those properties back on those galaxies, and we can see how far these galaxies are away from us, right? So thanks to the spectra, we were able to identify in this picture galaxies that are only a billion years when the universe was formed, right? So these are some of the earliest galaxies that we can find. We see now that the James Webb already have a record of some of the oldest galaxies seen in the universe, right? So this is amazing, just combining the images and the spectra, right? Looking at the rainbow of these galaxies. Another example of the James Webb capabilities, and we're talking about now, we already talk about these early stages of the universe. Now we want to talk about how planets form, how stars form, right? So we have a picture here, a beautiful picture of the Carina Nebula. It is taken with different cameras, with NIRCam and MIRI. And some of these, you can see all the details, all these features, all these streams of gas, all these cavities, all these bow shocks, everything. So these are basically stars, new stars that are being born, and they're pushing away material as they ionize all the media. Part of that material may collapse and form other stars. Some of these stars already have.
Of research is studying the formation of stars and planets in orbit around those stars. So I wanted to show you an artist's impression of what this environment might look like. Now we have really beautiful images of different specific components of these systems, but I hope by the end of the presentation, you'll see why it's hard to look at all of these things at once. So we have this really nice artist's impression that was made by scientists at the European Southern Observatory. And at the center of this image here, we have this ball that represents our very young, bright star. And this big ring, this brown ring of stuff, is what we call a protoplanetary disk. And this protoplanetary disk includes gas and dust and all of the constituents that will eventually be used to form planets. And if you look very closely in this image, you might see a couple of very young planets, very small planets that our artist has drawn in here. Now, when these young stars form, they form from the collapse of very large clouds in space. And something will disrupt those clouds, whether it's a nearby supernova explosion, a really massive star nearby that produces a lot of radiation that can disrupt this cloud. And the cloud will go from a very big kind of stable thing to a shrinking, collapsing ball. And so as the
元勋多媒体报道，谢收看。